In this session on vector analysis, we will discuss about scalar and vector products and gradient of scalar and its physical significance. Before the study of scalars and vectors, let us discuss about scalars and vectors. A quantity which is measurable is called as physical quantity, and all physical quantities are grouped into two types. One, scalar quantities, and another one, vector quantities or scalars and vectors. A scalar is the physical quantity which has only magnitude. Examples: length, speed, work, mass, density, electric charge, etc. Vectors are the another type of physical quantities which have both magnitude and direction. Examples: displacement, force, torque, acceleration, velocity, momentum, etc. Scalar product and vector product. Scalar product and vector products are the two ways of multiplying two different vectors, and these have most applications in physics and astronomy. First, the scalar product. The scalar product is also known as the dot product. The scalar product of two vectors is defined as product of magnitudes of the two vectors and the cosine of angle between them. This is the statement of scalar product or dot product law. If A and B are the two vectors and theta is angle between vector A and vector B, then we can write scalar product of A and B as vector A dot vector B is equal to AB cos theta. This is the mathematical representation of the scalar product or dot product, where mod of A is equal to A, mod of B is equal to B, where A and B are representing the magnitudes of the vector A and magnitude of the vector B. Example for the scalar product is work. Work is equal to vector F dot vector S, and work is a scalar quantity. Force is a vector, displacement is a vector, the product of two vectors is a scalar. That's why this dot product is also known as a scalar product. The scalar product or the dot product can be expressed as follows. If the same factors are expressed in the form of unit vectors, I cap, j cap and k cap are the unit vectors which are acting along x-axis, y-axis and z-axis respectively. Then we can write I cap dot I cap equal to j cap dot j cap equal to k dot k, or k cap dot k cap is equal to 1, because theta is equal to 0 degree, then cos 0 is 1. And also I dot j is equal to j dot k is equal to k dot I is equal to 0. In this case, theta is equal to 90 degree, cos 90 is 0. Therefore, I dot j equal to 0, j dot k equal to 0, k dot I is equal to 0. Next is vector product or cross product. Statement: the vector product of two vectors is defined as product of the magnitudes of the two vectors and the sine of the angle between them. If A and B are the two vectors and theta is angle between vector A and vector B, then vector product can be represented as vector A cross vector B is equal to AB sin theta into n cap, where n cap is unit vector in the direction of vector A cross vector B, and this represents the direction of resultant vector, that is A cross B, where mod of A is A and mod of B is B. They are representing the magnitudes of the vector A and magnitude of the vector B respectively. Examples: torque tau is equal to vector F cross vector R. And angular momentum is another example for vector product or a cross product, and is vector L is equal to vector P cross vector R. These are the two examples. In this case, the product of two vectors is a vector. That's why this cross product is also known as vector product. The product of two vectors is a vector. The vector product or cross product can be expressed as follows. The same vectors are expressed in the form of unit vectors I cap, j cap and k cap. And I cap, j cap, k cap are the unit vectors along x-axis, y-axis and z-axis respectively. Then we can write I cross I is equal to 0, j cross j is equal to 0, k cross k equal to 0, because theta equal to 0, sine 0 is 0. Therefore, I cross I equal to j cross j is equal to k cross k is equal to 0. And I cross j is equal to minus j cross I is equal to vector k. And minus I cap cross j cap is equal to j cross I, and j cross k is equal to minus k cross j is equal to I cap, and minus j cross k is equal to k cross j. Also, k cross I is equal to minus I cross k equal to j, and minus k cap cross minus I cap is equal to I cap cross k cap. Next, let us discuss about difference between scalar product and vector product. Scalar product is also known as a dot product. Vector product is also known as a cross product. Scalar product or dot product is product of magnitude of the vectors and cosine of angle between them. Cross product is the product of magnitude of the vectors and sine of the angle between them. The dot product is represented as vector A dot vector B is equal to AB cos theta. And vector product is represented as vector A cross vector B equal to AB sin theta into n cap. N cap represents the unit vector which represents the direction of vector A cross vector B. The resultant of the dot product of the vectors is always a scalar quantity. The resultant of cross product of the vector is a vector quantity. The dot product is 0 when the angle between two vectors is 90 degree. That is, when the vectors are orthogonal, the dot product is 0. The cross product is maximum when vectors are acting at an angle of 90 degree or the vectors are orthogonal, then the cross product is maximum. The dot product of two vectors, it follows commutative law, that is vector A dot vector B equal to vector B dot vector A. The cross product of two vectors does not follow the commutative law, that is vector A dot vector B is not equal to vector B dot vector A. Next is electromagnetic theory. Let us discuss about some of the basic points in the electromagnetic theory. First is field. Field is a space in which a physical quantity takes different values at different points. Scalar field and vector fields are the two types of fields. Scalar field is the space in which the physical quantity, that is scalar quantity, takes different values at different points. Examples for scalar field are electrical potential around a charged body, temperature around a hot body. Vector field is the space in which vector quantity takes different values at different points. Examples for vector field are electric field, magnetic field, gravitational field, etc. Next is differential operator or del operator. It is represented like this. Differential operator or del operator is defined as del is equal to differential operator is equal to I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z, where I cap, j cap and k cap are the unit vectors along x, y and z axis respectively. If the same differential operator is del operator is differentiated again is called as a Laplacian operator. It is represented as del square. Laplacian operator del square is defined as del square is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Gradient of a scalar function. If pi is the scalar function whose coordinates are x, y, z, and this pi of x, y, z is defined and differentiable at each point x, y, z in the region of the space, then gradient of the scalar function pi is grad pi is product of del and pi. Therefore, gradient of a scalar function grad pi is equal to del pi is equal to I dou by dou x plus j dou by dou y plus k dou pi dou z pi. After simplification, gradient of a scalar function grad pi is equal to del pi is equal to I dou pi by dou x plus j dou pi by dou y plus k dou pi by dou z, where I cap, j cap, k cap are the unit vectors along x, y and z axis respectively. The gradient of a scalar function is a vector quantity. Physical interpretation of gradient of a scalar function. Let us consider 2 points P and Q. P is the point which is having the coordinates x, y, z, and Q is having the coordinates, position coordinates x plus dx, y plus dy and z plus dz in the scalar field. The position vector, that is the vector distance from P to Q, that is dr. dr represents the position vector and is given by I cap dx plus j cap dy plus k cap dz, where I cap, j cap, k cap are the unit vectors along x-axis, y-axis, z-axis respectively. Let pi be the scalar function at point P and pi plus d pi be the scalar function at Q point. Then the change in the value of pi with respect to the distance dr is known as the total differential of pi, that is d pi by dr. Scalar value at P is pi. Scalar value at A is scalar value at P plus scalar value along x direction, that is x dx. Therefore, scalar value at A equal to pi plus dou pi by dou x dx, and scalar value at B is equal to scalar value at A plus change in this scalar function along y direction and is x dy. Therefore, scalar value at B is equal to pi plus dou pi by dou x dx. This is scalar value at A plus dou by dou y of pi plus dou pi by dou x into dx. This is scalar value at B. After simplification, the scalar value at B is equal to pi plus dou pi by dou x dx plus dou pi by dou y dy plus dou square pi by dou y dou x dx dy. The term dou square pi by dou y dou x into dx dy is small. Hence, this term is neglected. Therefore, the scalar value at B is equal to pi plus dou pi by dou x dx plus dou pi by dou y dy. Next is the scalar value at Q is equal to scalar value at B plus change of this scalar function along z direction, that is x dz. Therefore, scalar value at Q equal to pi plus dou pi by dou x dx plus dou pi by dou y dy. This is the scalar value at B. Already we calculated, plus dou by dou z of pi plus dou pi by dou x dx plus dou pi by dou y dy into dz. After simplification, we get scalar value at Q equal to pi plus dou pi by dou x dx plus dou pi by dou y dy plus dou pi by dou z dz plus dou square pi divided by dou z dou x dx dz plus dou square pi by dou z dou y dy dz. In this expression, these two terms, that is dou square pi by dou z dou x dx dz and dou square pi by dou z dou y dy dz are small. Hence, these two terms are neglected. Therefore, the scalar value at Q is equal to pi plus dou pi by dou x dx plus dou pi by dou y dy plus dou pi by dou z dz. This is equation 2. Therefore, scalar value at Q is equal to pi plus dou pi by dou x dx plus dou pi by dou y dy plus dou pi by dou z dz. Equation 1. And we know that scalar value at Q is pi plus d pi. Equation 2. From equation 1 and 2, we get pi plus d pi is equal to pi plus dou pi by dou x dx plus dou pi by dou y dy plus dou pi by dou z dz. Pi gets cancelled. Therefore, d pi is equal to dou pi by dou x dx plus dou pi by dou y dy plus dou pi by dou z dz. Equation 3. Now, del pi dot dr is equal to del pi is I dou pi by dou x plus j dou pi by dou y plus k dou pi by dou z dot dr is I dx plus j dy plus k dz. After simplification, we'll get del pi dot dr is equal to dou pi by dou x dx plus dou pi by dou y dy plus dou pi by dou z dz. Equation 4. From equation 3 and 4, we get RHS are same, therefore d pi is equal to del pi dot dr. Therefore del pi dot dr equal to d pi. Or we can write del pi vector dr r cap is equal to d pi, where r cap is the unit vector along dr direction. Del pi dot dr equal to d pi, or del pi dr r cap equal to d pi, or del pi r cap is equal to d pi by dr, where r cap is the unit vector along pq or along dr vector. Hence, it follows that gradient of a scalar function is maximum rate of change of scalar function along the direction which is same as position vector dr. This is physical interpretation of the gradient of a scalar function. Physical significance of gradient of a scalar function. From the physical interpretation of gradient of a scalar function, it follows that the gradient of a scalar function is the maximum rate of change of scalar function phi along the direction which is same as position vector. Then if gradient of a scalar function is positive along some direction, then scalar function increases along that direction. That is, scalar function increases if the gradient of a scalar function is positive in that direction. Next is, if gradient of a scalar function is negative along some direction, then scalar function decreases in that direction. If scalar function decreases, then the gradient of a scalar function is negative along that direction. Next physical significance of gradient of a scalar function is, if gradient of a scalar function is 0 along some direction, then the scalar function does not change along that direction. If the scalar function does not change along some direction, then gradient of a scalar function is 0 along that direction. These are the physical significance of gradient of a scalar function. Up to now, in this session, we discussed about scalar products and vector products and explanation. And we discussed about gradient of a scalar function, definition and its physical interpretation and physical significance of gradient of a scalar function. Thank you.